Today we're going to introduce capacitors and how they respond in DC circuits. We'll wait to see how capacitors respond in AC circuits until we introduce the concepts of reactance and impedance. For you is a DC circuit with two new symbols in it. You recognize the symbol for a battery and a resistor. The resistor is just there to show the resistance of the actual conductor in the entire circuit itself. But you have two new symbols. The first one over here is a switch, like a light switch. You'll notice that right now it's open, so no current is actually flowing through the system. Whenever this switch shuts, then current will flow. Over here, on the far right side, is a symbol for a capacitor. So what is a capacitor? Well, physically, it's two plates. If you zoom in really closely together, it's two plates separated by some type of insulator. Okay? So, if you think about what happens, can charge actually go across these two plates? Well, the answer is no. But what happens is the charge actually gets stored in the electric field between these two plates. What happens is when this switch shuts, you'll have current flowing from the battery to the capacitor. And that charge, those holes are going to build up on this plate surface here. So whenever those charges build up, that's actually going to store energy. It's like a short-term battery almost. And the voltage of the capacitor, based on the fact that it has stored electrostatic potential, so you're actually going to get a voltage that goes up and pushes back against your battery. So therefore, you can see that the longer we leave the switch shut, the higher the charge, and eventually the voltage of your capacitor is going to equal your voltage of your source, and current flow will stop. After that happens, current flow stops. Whenever we reopen the switch, however, if we reopen the switch, you're going to get all these stuff is going to discharge and it's going to equalize back. It's going to push back, it's going to discharge, and it's going to pull from the negative side, and it's going to pull negative particles back, negative particles back to equalize this voltage and cause this voltage to go down on the negative side. Okay? So you can think of it almost like a short-term battery. Another way to think of it is if you're a fluids person is if you have a pipe and you have a rubber membrane in this pipe. Okay? If you have water on both sides of it. Okay, this is with the switch open. As soon as you close the switch, let's say you have a pressure source over here. You have pressure. It pushes the water this way. Well, that membrane is going to bend. The more pressure, the more the membrane bends. And you still get water flow out of the other end of the pipe, although at a decreasing amount. All right? Until the pressure exerted by the membrane back on the source is equal to the pressure exerted by the source itself. And then whenever you cut the source off, which is the same thing as opening our switch in our electrical circuit, this rubber membrane is going to push back all that water and pull back all this water and return to its equilibrium position. So that's a fluids analogy for you on how a capacitor works. So let's delete that and define what capacitance actually is. So what is capacitance? Well, capacitance is simply Q over V. All right, so what is Q? V is pretty simple. C is pretty simple. C is capacitance. V is voltage. Q is the ratio of charge between the plates. Ratio of charge between plates. All right. So it's the ratio of the charge in between the plates. So that is capacitance. All right. Good stuff. And as you see, capacitors are used or can be used for a variety of different things. They can be used as filters. They're used extensively in radio circuits, and for AC applications, they're used to counteract inductance. They're used to filter out and smooth out voltage in DC circuits. They're used to tune radios. There's a large variety of uses for a capacitor, and this is one of the reasons you need to be familiar with them. All right. So what if we put capacitors in series and in parallel? Well, capacitors work the opposite of a resistor. So in parallel, capacitors all are all exposed to the same initial voltage, so therefore their capacitances add. So in parallel, capacitance total equals C1 plus C2 plus C3 all the way to C sub n. All right. In series, they're subject to the voltage on the other side of each one. So in series, 1 over CT equals 1 over C1 plus 1 over C2 plus 1 over C3 all the way to 1 over Cn. So notice that is the exact opposite of how resistors work. Okay, that's the easy way to remember that. So you can see, based on the fact that it has stored energy, there's a potential for work to be done. So what is the formula for work, and how does that actually occur? Well, work is done by the stored energy, by the stored charge. So we can actually take that, and based on the fact that it goes from 0 all the way to Q, which is the maximum stored charge, and it has directly related to voltage, we're going to integrate that curve with respect to the charge. Integrate voltage with respect to charge. It's going to give you out a few equal answers. The most common one, and the one that you need to know, is 1/2 CV squared. All right, that is the work done by a fully charged capacitor. Okay. Well, what about if you have a fluctuating voltage, like you're in the middle of charging the capacitor, or if you happen to be in an AC circuit? Okay. Well, in that case, you're actually going to have the stored energy also fluctuates. Hence, power must flow into or out of the capacitor. And the power can be found by taking the time derivative of the stored energy or the actual work done. So therefore, our power of the capacitor is defined as the time derivative of our work done, which is equal to the time derivative of 1/2 CV squared. You take the time derivative of that, that is going to be equal to the capacitance times the voltage as a function of time with respect to the derivative of the voltage as a function of time. Okay? So, now we need to find, in order to see what power, we need to find the actual function for V of t. Well, V of t is simply going to be equal to our Q of t over C. Remember, we just rearrange our capacitance equation. Q equals, or C equals Q over V. Well, we can just swap those two, and C is a constant, but voltage and charge can vary with respect to time, so we can redefine it as this equation. Well, what is that equal to itself? Well, that's going to be equal to 1 over C times the integral from T0 to T at any given point of I of tau with respect to tau plus V at time 0. Okay, so what is tau? All right, well, tau is actually going to be what's called the time constant of this circuit. Tau is the time constant, and we'll get into that shortly, what that exactly is. Okay, so tau is your time constant. Okay. Tau is their time constant. What about our current at the time? Well, our current is simply going to be directly related to charge. So our current is going to be our derivative of your charge with respect to time. Okay, so what's that going to equal? Well, that's going to equal C times derivative of your voltage with respect to time. Okay, so now we have all our formulas set out that you need to know, or most of them at least. But we can still expand this. We really don't know what our derivative of our voltage with respect to time and etc. are, and all these other things are. So how do we actually get this? What is our final bottom line? Well, if we apply Kirchhoff's voltage law, which we'll discuss in a later lecture, to our circuit that I had drawn in the very beginning, we'll show that V naught equals V of our resistor with respect to time plus V of your capacitor with respect to time. Note that as the current goes down, remember I said that initially the capacitor has zero charge on this plate, so it's not going to be pushing back. As the voltage on the capacitor builds, your voltage drop across the resistor is going to go down because there's going to be less current flowing through that. Remember, V equals IR, so whenever current goes down, your voltage drop across that resistor is also going to go down. Alright, so your voltage of your source is going to be equal to your voltage of your resistor plus your voltage of your capacitor with respect to time. Well, so like I said, that is going to be equal to the current flowing through your resistor with respect to time times your resistance. So V equals IR, so this is I at any given point in time times your resistance, plus our V of t, which we found earlier to be 1 over C T0 to any given t of I of tau d tau, time constant. All right. If you take the derivative and multiply by C, it gives a first order differential equation. So if you take the derivative and multiply by C, you can get a first order differential equation, and this is the differential equation that is going to derive our overall current and voltage equations. So if you do that, you're going to get RC times the derivative of current with respect to time plus current with respect to time equals 0. And from that, we can actually get I with respect to t, or I of t, equals V naught, or V of your source, over R, e to the negative t over tau, where tau is your time constant. Okay? And V of t is going to be given by V naught times 1 minus e to the negative t over tau. Okay? Tau at time 0, so tau at 0 equals RC. All right, so that is actually going to be your time constant. So RC is given as your time constant of the system. As the capacitor reaches equilibrium with the source voltage, the voltage across the resistor and the current through the entire circuit decay exponentially away. Okay. In the case of a discharging of a charged capacitor, likewise demonstrates exponential decay, but with the initial capacitor voltage replacing your source voltage and the final voltage being 0.